So the first of the tracks that we're going to look at in the material is kind of the concrete computational sort of side of linear algebra, where the reduced row echelon form of a matrix that's been augmented to represent a system of equations still reigns supreme. So all of those topics that we learned in the first chapter about the relationship between a linear system of equations and a vector equation and an augmented matrix, all of that is still in the mix. Solving those equations and describing the nature of their solutions, whether they're consistent or inconsistent, and how many solutions do they have, all of that is still in play on our computational track. And today that computational track is represented by the work we're going to do around linear independence and basis for a vector subspace. And I think we've already alluded a little bit to a couple of those topics in some of our earlier work. We talked about spanning sets. It's sort of spanning sets is the other side of the coin of linear independence. So what we're going to hopefully be able to see by the end of the day today on that track is that a basis for a vector subspace is kind of the smallest possible collection of vectors that still spans the entirety of my subspace. But it's also the largest possible set of such vectors that doesn't do so in a redundant fashion. In other words, it's the largest possible subset of those vectors such that if I take away any one of those vectors, I'm not going to be spanning the whole thing anymore, right? So a basis is sort of the smallest possible spanning set and the largest possible set of what we call linearly independent vectors that is sufficient to describe a vector space entirely. What's great about a basis is that for a given vector space, every basis that we could come up with, and we can come up with infinitely many, it turns out, but every basis we can come up with is going to have the same number of vectors in it. And so the number of vectors in a basis for a vector space is an invariant quantity of the basis that we select. And it's a number called the dimension of our vector subspace. So that means that we'll finally be able to do something today that you've probably done informally for a very long time in your mathematics and geometry education. And that's assign the word dimension to something. Oh, this is a two-dimensional thing. This is a four-dimensional thing. There's always been kind of a vagueness with which you use that term until today, when dimension is going to mean something very specific that carries over into all those other meanings that we've used the word dimension for in our mathematical past. It is the number of vectors in a basis for a vector space or a vector subspace. So that's the computational side of what we're working on today. On the theoretical side, we had a great, I thought, discussion a week ago about proofs and sort of the abstract forms of reasoning in mathematics and what makes a proof effective, what makes a proof communicate well, what are some of the individual elements and sort of beats that an effective proof goes through. All of that material is still very much in our minds, or should be in our minds. And today we're going to actually tackle using those sorts of ideas and bringing them to bear on some theoretical linear algebra questions. And so this is on the theoretical side where we're hardly going to be computing any reduced row echelon forms of anything. Instead, what we're going to be spending our time doing is really popping the hood of linear algebra and figuring out, well, what is it that really makes linear algebra work? What is it that makes it linear algebra? Where else can we find linear algebra besides just in thinking about the ordinary ways that we pick up vectors as being, points or arrows inside of a Euclidean space, and addition, meaning that we just add using ordinary arithmetic the components of my vectors, and scalar multiplication, meaning I just take an ordinary real number and I multiply it by each of the components of my vectors. That's the standard viewpoint of what finite dimensional linear algebra is. But there's so much more to it than that. And so this is our first real opportunity, I think, to look at something in mathematics as a structure rather than as a concrete collection of objects. One of the questions one of the teams asked in the Discord chat over the last week is they were looking at some of the V1 problems on vector spaces in practice and in the quiz that's been open, and asking, well, are we going to get to a point where we can define what the authors of our book mean by the funny circled plus sign and the funny circled multiplication sign? And my answer was, no, we're not going to define those things because they're deliberately meant to be generalities, right? What we're supposed to look at when we're assessing whether or not a mathematical structure is a vector space is however that funny addition and funny multiplication are being defined, do they walk and talk and quack just like the kinds of addition and scalar multiplication we would expect to find in a real honest-to-goodness vector space? And if they do, then whatever their definition was, that structure is still going to qualify as a vector space. We can still use the ordinary tools of linear algebra to study that system without having to worry that we're doing something illegal, right? As long as the vector space we study really satisfies the properties we need vector spaces to satisfy, it doesn't matter what the particulars are. We can still do linear algebra in all the same ways. We just have to remember that adding might mean something different than our ordinary addition. Scalar multiplication might mean something different than our ordinary scalar multiplication. So the statement that we can only do linear algebra on vector spaces is a tautology, in the sense that linear algebra is by definition the study of vector spaces and their properties. And so there's a sense in which every subdiscipline of mathematics is about sort of what are the objects that we're studying, and then what are the functions that connect those objects to one another. Do I have the book on my desk? I think it fell off behind my desk, unfortunately, but I have a great book. It's called Category Theory in Context, and it's an upper level mathematics book. But category theory is kind of the study of mathematics per se, like what makes mathematical structure. And it turns out that the easiest way to describe what makes a mathematical structure is that we have objects, we have things, we have nouns, and then we have functions, morphisms, things that connect one of those objects to another. We might think of those as the verbs, right? So we have nouns, we have verbs, and we can study sentence structure. So in linear algebra, the nouns are vectors. And the verbs, the functions, the morphisms, are functions that preserve the structure of vector spaces. We're going to call those linear transformations when we get to the next chapter. So vectors and linear transformations, those two things together are what make linear algebra linear algebra. And it just so happens that in finite dimensional vector spaces, linear transformations can be represented by a matrix, and that's where matrices come into the picture for us. So that's the ultimate goal for us, is to get a little bit more exposure and a little bit more practice with those abstract reasoning ideas by deploying them in the service of writing a few proofs that relate to the theoretical ideas of linear algebra. So I think that's probably the place we're going to start, is sort of start by thinking abstractly, expansively, thinking in generalities and thinking about proof. And in doing so, we'll talk about vector spaces. So what is the type of structure that typifies a vector space? And then vector subspaces, which, as the name suggests, are just vector spaces within vector spaces, right? So sort of smaller examples of vector spaces that live within larger vector spaces. We would call those vector subspaces. For a first course in linear algebra like ours, most vector spaces that we're going to study are finite dimensional. We're also talking about dimension a little bit later on today. And in the finite dimensional case, a finite collection of vectors is all that we need in order to describe by their span the entire vector space. And it's also what lets us write down a matrix with only finitely many rows and columns to represent a linear transformation between finite dimensional vector spaces. So subspaces have to follow all the same rules that a vector space follows. They are vector spaces in their own right. And the only restriction is that to say that something is a vector subspace of something means that the addition and the scalar multiplication, in big scare quotes, on the subspace are defined in the same way that they're being defined on the larger space. That's the only restriction that we have on it. So we can't put different kinds of arithmetic on a subset of a vector space and then try to call that subset a subspace.